In the frozen expanse of northwestern Russia, silence reigns. It is a silence of immense scale, broken only by the whisper of wind across endless birch forests and the low, electronic hum of a nation on high alert. Here, at the Plesetsk Cosmodrome, the Soviet Union watches the sky, its gaze fixed on the heavens, perpetually searching for threats from its ideological adversary an ocean away. The date is March 6, 1970, USSR. The Cold War is not merely cold. It is a glacial standoff, a conflict waged not in open battle, but in the shadows, in the laboratories, and on the glowing phosphorescent screens of radar installations like this one. Inside the concrete bunker, the air is thick with the smell of ozone and stale cigarette smoke. Men in uniform, their faces etched with the focused boredom of routine, sit before their consoles. Their world is one of ordered, predictable physics. They track the graceful arcs of satellites, the lumbering paths of American bombers on patrol near their borders, the familiar signatures of weather balloons. Everything has a place, a known speed, a defined ceiling. The laws of aerodynamics and jet propulsion are as immutable and comforting as the laws of gravity. They are the gatekeepers of Soviet airspace, and they believe, with the certainty of men trained in mathematics and military doctrine, that nothing can enter this sanctum without their knowledge and permission. Then it appears. A single, ephemeral blip on the edge of detection. It is not like the others. At first, it is dismissed as a ghost, an atmospheric anomaly, a glitch in the machine. Senior Lieutenant Viktor Petrov, a man whose eyes have traced the paths of American aircraft for 15 years, leans closer. His experience tells him this is an error. His instruments, however, tell him a different, terrifying story. The contact is moving at a velocity that defies logic. The data streaming back to his console paints a picture of an object climbing through the stratosphere at a rate that should tear any known aircraft apart. It is higher than the U-2 spy planes they had mastered shooting down. It is faster than the ballistic missiles they tracked during test launches. Petrov adjusts the gain, trying to resolve the signal. The blip is faint, inconsistent. It flickers, sometimes vanishing for seconds at a time, only to reappear dozens of miles from its last known position. It does not behave like an aircraft. It behaves like a phantom, a specter moving through their skies with impunity. Across the vast, interconnected network of the Soviet Air Defense Forces, the PVO, other operators are seeing the same impossible thing. Reports flood the command channels, laced with a mixture of confusion and disbelief. The target is painting on screens from the Barents Sea to the Arctic Circle, streaking across their territory at over 2,000 miles per hour and at an altitude exceeding 80,000 feet. No aircraft in the world flies like this. The Americans, their intelligence had assured them, did not possess such a thing. It was, according to the finest minds in Soviet aviation science, a physical impossibility. Petrov reaches for the secure telephone, his hand steady, but his mind racing. The call he is about to make to Moscow will be more than a routine report of an airspace violation. It will be an admission of impotence. It will be the first tremor of a seismic shock that will ripple through the entire Soviet military-industrial complex. What he and his comrades are witnessing is not just an aircraft. It is the death of an assumption. The death of certainty. For decades, the Soviet Union had built its military identity on a foundation of unshakable confidence. Confidence in their engineering, confidence in their defenses, and confidence in their understanding of their enemy's limits. In the Kremlin, generals had scoffed at rumors of American experimental projects, secure in the knowledge that the laws of physics were the same in California as they were in Moscow. They had calculated the brutal realities of heat, friction, and fuel consumption at high speeds and concluded, with sound logic, that the American ambition had outstripped its capability. They had, in essence, laughed. That laughter died on March 6, 1968. It died in the quiet confusion of 1,000 radar rooms as an unknown entity vanished from their screens at Mach 3, leaving behind only a lingering question mark in the sky and a deep, chilling dread in the hearts of those who watched it go. This is not simply the story of a remarkable aircraft, the SR-71 Blackbird. To frame it as such is to miss the point entirely. This is the story of how that aircraft became a psychological weapon of devastating effectiveness, a tool that did more than gather photographs from the edge of space. It shattered the foundational myth of the Cold War, the myth of Soviet technological parity. It proved that a nation's most formidable defenses are not its missiles or its interceptors, but its own assumptions. The appearance of the Blackbird was the first domino in a chain reaction that would force a painful reevaluation of Soviet science, trigger a ruinously expensive new arms race, and expose the deep, systemic cracks in a superpower's confidence. This is the story of how a machine, born from a radical philosophy in a secret desert facility, managed to psychologically dismantle an empire from 16 miles up without ever firing a single shot. It is the story of what happens when the impossible becomes real, and a nation is forced to confront the terrifying reality that it is no longer in a race with its rival, but is instead watching them disappear over the horizon. To understand the depth of the shock the SR-71 delivered, one must first understand the world that existed before it. One must inhabit the mindset of the Soviet leadership in the mid-1960s, a mindset forged in the crucible of war and hardened by decades of ideological struggle. This was not a leadership prone to self-doubt. The Union of Soviet Socialist Republics saw itself as a global titan, an industrial and scientific powerhouse that had risen from the ashes of the Second World War to challenge the United States for dominion over the planet. Their confidence was not baseless bravado. It was earned. It was the Soviets who had put the first satellite, Sputnik, into orbit, a technological coup that sent a wave of panic through the American establishment. It was the Soviets who had sent the first man, Yuri Gagarin, into the cosmos, proving their mastery over the heavens. Their nuclear arsenal was vast and terrifying, capable of incinerating the West. Their conventional forces in Europe dwarfed those of NATO, a seemingly unstoppable red tide of tanks and soldiers. In the minds of the men in the Kremlin, the technological race with America was a contest of equals, a neck-and-neck marathon where one side might pull ahead momentarily, only to be matched and surpassed by the other. This belief in parity was the central pillar of their strategic doctrine. Nowhere was this confidence more pronounced than in the realm of air defense. The PVO, the Soviet Air Defense Forces, was more than just a branch of the military. It was a national obsession. The sheer scale of the Soviet Union, with its 11 time zones and vast, often indefensible borders, necessitated the creation of the most extensive and sophisticated air defense network the world had ever seen. It was a layered fortress, a technological wall built to seal the nation's airspace. The outer layer consisted of a sprawling network of early warning radar stations, like the one at Plesetsk, designed to detect intruders hundreds of miles away. Closer in, a dense belt of surface-to-air missile, or SAM, sites stood ready. These were the dreaded SA-2 guideline missiles, the very weapons that had reached up to 70,000 feet and torn Francis Gary Powers' U-2 spy plane from the sky in 1960. That event, the downing of Powers, was a seminal moment for the Soviet psyche. For years, the high-flying American U-2s had crisscrossed their territory with impunity, untouchable specters photographing their most secret military installations. The inability to stop these flights was a source of deep national humiliation. When their engineers finally developed a missile that could reach that altitude, the shoot-down was not just a military victory, it was a profound ideological and propaganda triumph. Premier Nikita Khrushchev brandished pieces of the wreckage at the United Nations, a tangible symbol of Soviet ingenuity and strength. The message was clear. The skies over the Soviet Union belonged to the Soviets. The incident hardened their resolve and calcified their assumptions. They had met the pinnacle of American reconnaissance technology and had defeated it. They concluded, logically, that any future American efforts would be evolutionary, not revolutionary. The next spy plane would be a little faster, a little higher, but it would still be fundamentally bound by the same physical constraints. Their own engineers reinforced this belief. Soviet aviation philosophy was deeply rooted in pragmatism, brute force, and iterative design. They built machines that were rugged, powerful, and produced in massive numbers. The apotheosis of this philosophy was the Mikoyan-Gurevich MiG-25, codenamed Foxbat by NATO. When Western intelligence first caught glimpses of this colossal interceptor, it caused a panic. Its massive wings and enormous engine intake suggested a superfighter of unparalleled performance. And in some ways, it was. The MiG-25 was a monster of stainless steel, capable of rocketing to incredible altitudes and achieving bursts of speed in excess of Mach 3. It was designed with a single purpose in mind: to climb at a phenomenal rate and shoot down the high-altitude, high-speed bombers and reconnaissance aircraft the Americans were rumored to be developing. But the MiG-25 was also a perfect reflection of Soviet technological limits. It was a sledgehammer in an age that would soon demand a scalpel. Its powerful Tumansky engines could only sustain their maximum speeds for a few minutes before they would overheat and tear themselves to shreds. Pushing the aircraft to its absolute limits often meant the engines had to be replaced entirely after the flight. It was an interceptor, not a cruiser. It could make a desperate, breathtaking dash to the edge of space, but it could not live there. Its radar was powerful but primitive, a blunt instrument designed to burn through enemy jamming with sheer wattage. Soviet metallurgists, working with the materials available to them, had to use heavy steel alloys to cope with the heat of friction, resulting in a plane that was powerful but not particularly agile. The Soviet scientific establishment, therefore, looked at the problem of sustained high-speed flight and saw an insurmountable wall of physics. They knew, because their own brilliant engineers had told them so, that at Mach 3, air friction would heat an aircraft's skin to temperatures that would weaken steel and melt aluminum. They knew the fuel consumption would be astronomical, requiring an impossibly large aircraft. They knew the challenges of creating engine components that could operate reliably in such a punishing environment. And because they themselves could not solve these problems in a practical, operational way, they projected their own limitations onto their adversary. They assumed the Americans were grappling with the same brutal equations and arriving at the same conclusions. The reports from their intelligence networks seemed to confirm this. They saw incremental improvements to existing bomber fleets, new variants of fighter jets. They saw nothing that suggested a quantum leap was imminent. The antagonist in this story, then, was not a person or a nation. It was a belief system. It was the deeply entrenched, institutional myth of technological parity, a myth born of past successes and confirmed by a limited understanding of their rivals' true philosophy of innovation. It was a fortress of certainty, and it was about to be breached, not by an army, but by a single, impossible machine. While Moscow's finest minds were confidently defining the boundaries of the possible, a very different kind of thinking was taking place 6,000 miles away in the sun-scorched landscape of Burbank, California. Here, hidden behind a veil of secrecy so absolute it bordered on paranoia, was a facility that operated outside the normal rules of corporate and military bureaucracy. It was officially the Lockheed Advanced Development Projects Division, but everyone knew it by its legendary moniker, the Skunk Works. And its presiding genius was a man named Clarence Kelly Johnson. Kelly Johnson was not a man who respected conventional limits. His design philosophy was captured in his famous motto, "Be quick, be quiet, and be on time." And he ran his Skunk Works as a fiefdom of innovation, a place where a small, hand-picked team of brilliant engineers were given immense autonomy. insulated from red tape, and tasked with achieving the impossible. When the CIA came to him after the U-2 program, their request was simple in its audacity. They needed a new reconnaissance aircraft. This one had to fly so high and so fast that it could never be shot down. It had to be, for all intents and purposes, invincible. For Johnson and his team, this was not a matter of making a better U-2. It required them to wage a war against physics itself. The first and most formidable enemy was heat. As an aircraft pushes through the atmosphere at supersonic speeds, the compression and friction of air molecules generate incredible temperatures. At Mach 3, an aircraft's leading edges can reach over 800 degrees Fahrenheit, while the main body soaks at 500 to 600 degrees. This realm of flight is known as the thermal thicket, a barrier where conventional materials like aluminum, the workhorse of aviation, lose their structural integrity and begin to behave like soft plastic. The MiG-25 had solved this by using heavy nickel-steel alloy, but this was a brute force solution that came with a massive weight penalty. Johnson knew he needed a different material, something light, strong, and almost impervious to heat. The answer was titanium. But in the late 1950s, titanium was an exotic, temperamental metal. It was difficult to mine, incredibly expensive, and a nightmare to work with. It became brittle if contaminated by impurities during welding, and conventional tools would shatter against its hardness. The biggest problem, however, was supply. The world's largest supplier of high-grade titanium ore was the Soviet Union. In one of the greatest ironies of the Cold War, the CIA, through a series of shadowy front companies and third-party agents, began purchasing vast quantities of titanium from the very adversary the future aircraft was being designed to spy on. Soviet officials, unaware of its final destination, were effectively selling the raw material for the weapon that would later render their defenses obsolete. Even with the material secured, the Skunk Works team had to invent entirely new manufacturing techniques. They developed specialized welding methods in argon-filled chambers and created tools and drill bits capable of machining the stubborn metal. The entire airframe of the aircraft, which would become known as the A-12 and later the SR-71, would be constructed from a titanium alloy, comprising over 90% of its structure. Its very skin was designed to be a heat sink, glowing a dull cherry red in flight as it absorbed and radiated the ferocious temperatures of hypersonic travel. The next impossible problem was propulsion. An aircraft at 85,000 feet is flying in an atmosphere so thin it is practically a vacuum. A conventional jet engine would suffocate from lack of oxygen. Furthermore, an engine powerful enough to reach Mach 3 would be incredibly inefficient at slower subsonic speeds. The solution, developed by Pratt & Whitney, was a masterpiece of engineering: the J-58 engine. It was not a single engine, but a complex hybrid system. At low speeds, it functioned as a relatively conventional afterburning turbojet. But as the aircraft accelerated past Mach 2, a series of massive cones in the engine inlets would move, and sophisticated bypass doors would open. These changes would divert the supersonic airflow around the core of the turbojet and directly into the afterburner, effectively transforming the engine into a high-efficiency ramjet. The J-58 was a mechanical chameleon, an engine that changed its very nature in mid-flight. The complexity was staggering, but it worked, allowing the Blackbird to cruise at speeds over 2,200 miles per hour for hours on end, something Soviet engineers had deemed physically impossible. But speed and altitude were only part of the equation for invincibility. Kelly Johnson knew that the future of aerial warfare belonged to those who could control the electromagnetic spectrum. The aircraft had to be as invisible as possible. This was decades before the term stealth entered the public lexicon. Johnson's team pioneered concepts that would become foundational to stealth technology. The Blackbird's unique shape was not chosen for aesthetics. Its long, flat fuselage, blended wings, and inwardly canted twin tails were all meticulously designed to deflect radar waves away from their source rather than reflecting them back. The leading edges of the wings, known as Chinese, created lift and also helped to scatter radar energy. Furthermore, the aircraft was coated in a special iron ferrite-based paint that was designed to absorb radar waves, converting their energy into a minuscule amount of heat. It wasn't true stealth in the modern sense of the F-117 or B-2, but it dramatically reduced the aircraft's radar cross-section. To a Soviet radar operator, the massive 107-foot-long Blackbird would appear on screen as a target no larger than a small bird, if it appeared at all. Finally, there was the human element. Flying at the edge of space meant the pilots were, in essence, astronauts. They wore fully pressurized spacesuits identical in many ways to those worn by the Mercury astronauts. The cockpit was a self-contained life support system. Even the fuel was exotic. A special formulation called JP7 was developed, with a high flash point required to withstand the incredible temperatures of the airframe. This fuel was so stable it wouldn't ignite with a match. To start the engines, a chemical ignition system using triethylborane, a substance that explodes on contact with air, had to be injected into the engine. Because the titanium airframe expanded significantly due to heat in flight, the fuel tanks were designed to leak on the ground. A Blackbird sitting on the tarmac would constantly weep fuel onto the runway, its tanks only sealing themselves once the aircraft was airborne and heated to operating temperature. On December 22, 1964, test pilot Robert Gilliland pushed the first SR-71 through Mach 3. Everything held. The engines roared, the titanium skin glowed, and the impossible became a reality over a secret test range in the Nevada desert. While Soviet generals were reading intelligence reports about incremental improvements to American bombers, the Skunk Works had not just built a new aircraft. They had created a new category of existence. They had weaponized the frontiers of material science, propulsion, and electromagnetics. This was the turning point. This was the secret that once unleashed would not just overfly Soviet territory, but would shatter the very foundation of their technological confidence. The myth of parity was about to collide with a 70-ton titanium reality. The first overflights of the SR-71 were met not with alarm, but with confusion and denial within the Soviet high command. The initial reports from radar operators like Senior Lieutenant Petrov were so far outside the realm of accepted performance that they were systematically dismissed. The official explanations ranged from high-altitude weather phenomena to equipment malfunction or even mass hypnosis among radar crews. The data simply did not fit their reality. No aircraft could sustain those speeds. No aircraft could operate at those altitudes. The flickering, ghost-like signature on the radar screens was, by definition, an error. The alternative, that the Americans had secretly achieved a multi-generational leap in aviation technology, was too disturbing to contemplate. But the anomalies persisted. The ghosts kept appearing, always along the sensitive borders of the Soviet Union, over the Kamchatka Peninsula, the Kola Peninsula, the Baltic states. They would appear on radar 200 miles offshore, accelerate with impossible speed, climb into the ionosphere, and then paint a precise, deliberate line across a classified submarine base or a missile testing range before vanishing back into international airspace. The missions were surgical, brazen, and untouchable. Scrambled MiG-25s would rocket upwards in pursuit, their pilots pushing their fragile engines to the breaking point, only to see the contrails of the intruder still miles above them, pulling away effortlessly. Soviet missile crews would achieve a radar lock for a few precious seconds, only to watch in frustration as the target outran their fastest SAMs, exiting the missile's engagement envelope before the launch sequence could even be completed. The psychological toll on the elite pilots and air defense crews of the PVO was immense. These were the best of the best, the guardians of the motherland, equipped with what they had been told was the world's most formidable hardware. Yet, they were utterly helpless. One MiG pilot, Major Alexei Belov, famously reported getting a visual on the Blackbird, a dark, menacing shape with no visible wings, only to watch it accelerate away as if his own aircraft were standing still. The experience was profoundly demoralizing. It was a recurring demonstration of not just inferiority, but of utter irrelevance. Their best efforts were futile gestures against a foe operating in a different physical dimension. The turning point in Soviet understanding, the moment of true chilling realization, came when their analysts conducted a forensic breakdown of the radar data. The twist was not simply that the Blackbird was fast and high. The truly devastating discovery was that it was also a master of deception. Declassified reports from defecting Soviet engineers later revealed the moment they understood the aircraft was actively manipulating their systems. A technician at the Semipalatinsk test site, analyzing recordings of the overflights, noticed that the radar signature was not just small, it was dynamic. It changed. The SR-71 was equipped with a sophisticated suite of electronic countermeasures, ECMs, that could analyze an enemy radar signal and instantly broadcast a modified signal back. It could make itself appear larger or smaller, faster or slower. It could project multiple false targets onto the screen, sending interceptors on a wild goose chase. Most effectively, it could make itself vanish entirely, a capability that convinced operators their equipment had failed. The laughter of the generals in Moscow had long since faded, replaced by a grim silence. They had prepared for an enemy they could see and shoot. They were now facing an enemy that could decide whether or not it wanted to be seen at all. The Blackbird wasn't just evading their defenses, it was playing with them, actively subverting their perception of reality. This revelation sent a shockwave through the Soviet establishment. The technological gap was not a simple matter of speed or materials. It was an electronic, computational, and systems integration chasm. This triggered the first domino. Marshal Andrei Grechko, the Minister of Defense, ordered a massive, top-priority program to counter the SR-71. This was not a request for proposals. It was a desperate, state-level command to close the gap at any cost. The Soviet military-industrial complex, a behemoth built for mass production of proven designs, was violently retasked. Resources were siphoned from dozens of other programs. The Mikoyan Design Bureau was ordered to create a new interceptor, an evolution of the MiG-25, which would eventually become the MiG-31 Foxhound. This new aircraft would have a more powerful radar capable of look-down, shoot-down engagement and longer-range missiles. The development of new surface-to-air missile systems, like the S-200 and the nascent S-300, was dramatically accelerated. These were designed specifically with the Blackbird in mind, featuring higher ceilings and faster projectiles. It was a frantic, ruinously expensive effort to build a shield against a single American weapon system. The second domino to fall was in intelligence. The KGB and GRU were tasked with the impossible: steal the secrets of the Blackbird. Soviet agents across the globe were activated. Their missions refocused on penetrating Lockheed, Pratt & Whitney, and the constellation of contractors involved in the program. But the Americans, having learned from past security breaches, had compartmentalized the SR-71 project to an unprecedented degree. Workers at the Skunk Works often only knew the specific part they were building, with no concept of the whole. Technical manuals were fragmented. Security was absolute. The Soviet espionage machine, one of the most effective in the world, slammed into a brick wall. They could gather no meaningful technical intelligence, leaving their engineers to try and reverse engineer the aircraft's capabilities from the frustratingly limited data of its overflights. The final, and perhaps most significant, domino was systemic. The crisis forced a painful moment of introspection within the Soviet leadership. The Blackbird was not an anomaly. It was a symptom of a deeper problem. It was the product of a different philosophy. While Soviet design bureaus favored a conservative evolutionary approach, perfecting individual components before integrating them, the Americans at Skunk Works had pursued a revolutionary systems-based approach. They had advanced propulsion, materials, science, aerodynamics, and electronics simultaneously, integrating them into a single platform where the whole was far greater than the sum of its parts. This realization was an indictment of the entire Soviet system of research and development, which was seen as bureaucratic, risk-averse, and stifling to radical innovation. The Blackbird proved that America's real advantage was not just its technology, but its ability to imagine, to take enormous risks, and to manage immense complexity to achieve a breakthrough. For the aging ideologues in the Kremlin, this was a more terrifying threat than any weapon. It suggested that the very structure of their society was ill-equipped to compete in the next phase of the technological arms race. The black jet, flying silently overhead, was casting a long shadow of doubt over the future of the entire Soviet project. The SR-71 Blackbird would continue its operational life for another 3 decades, but its most profound impact had already been made in those first few years. It never fired a weapon. Not a single Blackbird was ever lost to enemy action, despite over 4,000 attempts by hostile forces to shoot it down. Its true legacy is not measured in combat statistics, but in the silent strategic shifts it caused on the ground below. For 25 years, it was the United States' ultimate ace in the hole, a strategic reconnaissance asset that provided presidents with unparalleled intelligence during every major crisis, from the Vietnam War to the Yom Kippur War to tensions in Libya and North Korea. The photographs and electronic intelligence it gathered allowed American policymakers to look directly into the heart of the Soviet war machine, tracking the development of new submarines, the deployment of nuclear missiles, and the disposition of their armies. It removed guesswork from geopolitics, replacing it with hard thus visual evidence. For the Soviet Union, the legacy was far more painful. The desperate multi-billion-ruble effort to counter the Blackbird became a massive drain on an already strained economy. The development of the MiG-31 and the S-300 missile system were incredible engineering achievements in their own right, but they were fundamentally reactive. They were answers to a question the Americans had posed a decade earlier. By the time these systems were fully deployed, American technology had already moved on, focusing on the next generation of stealth with the F-117 and the B-2 bomber. The SR-71 had locked the Soviets into a perpetual game of technological catch-up, forcing them to expend vast resources to counter a threat that, by its very existence, proved they were already years behind. Some historians argue that this strategy of technological exhaustion, forcing the USSR into unsustainable defense spending, was a significant contributing factor to the economic decay that precipitated its eventual collapse in 1991. The Blackbird didn't just photograph Soviet military sites, it photographed the cracks in the foundation of the Soviet economy. The universal lesson of the SR-71 is a timeless and sobering one about the profound danger of technological hubris. It demonstrates how a nation, even a superpower at the peak of its strength, can be strategically paralyzed by its own rigid assumptions. The Soviet Union's leadership was blinded by their own successes. They believed they understood the rules of the game, only to discover their opponent was playing an entirely different game altogether. The Blackbird is a monument to the power of asymmetrical advantage, not an advantage in numbers of tanks or missiles, but an advantage in thought, in daring, and in a culture of innovation willing to pursue the seemingly impossible. It proves that history can be turned not by the roar of cannons, but by the quiet work of a small group of engineers who refuse to accept the word impossible. This lesson echoes with unnerving clarity in our modern world. The Blackbird of the 21st century may not be a titanium aircraft. It might be a revolutionary artificial intelligence algorithm that can cripple a nation's infrastructure without firing a shot. It could be a breakthrough in quantum computing that renders all current cryptography obsolete overnight. It could be a bioengineered weapon, or a swarm of autonomous drones that redefines the very concept of a battlefield. Nations today continue to invest trillions in conventional military hardware, aircraft carriers, fighter jets, and tanks, while the next truly disruptive, paradigm-shifting threat may be gestating silently in a university lab or a tech startup's garage. The story of the SR-71 serves as a permanent warning. The greatest threat is often the one you have failed to imagine. It is the capability that your own experts have dismissed as science fiction. And in the end, the SR-71 Blackbird retired from service, a relic of a bygone era of superpower confrontation. Its sleek, alien form now rests silently in museums, a testament to a time when human ingenuity was pushed to its absolute limits. But its story is more than just a chapter in aviation history. It is a parable. It speaks to the fragility of power and the arrogance of certainty. The aircraft that Soviet generals laughed at did more than just vanish from their radar screens. It vanished into a future they could not comprehend, leaving them in a present they could no longer defend. It was a black specter on the edge of space, a silent messenger from tomorrow, serving as an eternal reminder that the ultimate high ground is not measured in altitude, but in imagination. And in the long, cold war of ideas, it is the imagination that will always, ultimately, claim victory.